Okay, so get this. We're diving into something truly mind-bending.
Oh, yeah.
Gravitational waves. You know those ripples in space-time? Einstein predicted those.
Right.
Well, what if they aren't ripples at all?
Oh, okay.
What if gravity is actually a push force? I know, I know, it sounds crazy.
Yeah.
But that's exactly what we're exploring today. We're taking a deep dive into excerpts from Gravitational Waves, a vacuum push perspective
Okay.
by Larkey.
Got it.
This deep dive is your shortcut
Shortcut
to understanding this wild new theory about gravity.
Awesome.
So Einstein's theory,
Okay.
which most of you are probably familiar with,
Hmm?
says that massive objects warp space-time around them.
Right.
Think of a bowling ball on a trampoline.
Okay.
Makes a dip, nearby objects roll towards it.
Yeah.
That's kind of how gravity works, according to Einstein.
I see.
And gravitational waves are like
Like
ripples that spread out from those warped regions when something big accelerates,
Okay.
like two black holes collide.
Right. Now, the SMF RVS model
Okay.
stands for subtle magnetic field and vacuum scalar field.
Yeah.
Proposes a totally different mechanism.
Okay.
Suggests that gravity is actually
A push force.
a push force arising between these two fields.
Okay, and here's the kicker.
Yeah.
Both theories,
Both.
ripples in space-time versus this vacuum push, can actually explain the same gravitational wave signals that scientists are detecting
No way!
with instruments like LIGO and Virgo.
So, two completely different explanations,
Yeah.
but they predict the same outcome.
How is that even possible?
It's like two chefs
Okay.
creating the same dish using completely different ingredients and techniques. The math behind both theories is incredibly complex.
Yeah.
But even though the underlying mechanisms are vastly different, they produce remarkably similar predictions for how gravitational waves behave.
No.
At least for now, our instruments aren't sensitive enough to measure the subtle differences between the two models.
So how can we
figure out?
Yeah, how can we figure out which theory is actually right?
Yeah. That's where things get really exciting.
Exciting.
There are a few potential tests
Okay.
that could help us differentiate between the two.
All right.
Think of it like a cosmic detective story,
Okay.
where we're looking for tiny clues
Yeah.
that reveal the true nature of gravity.
I'm intrigued. What kind of clues are we talking about?
Well, one key difference lies in how the two models predict the behavior of extremely fast-spinning black holes.
So fast-spinning black holes?
Yeah.
Okay.
Einstein's theory says there's a limit how fast a black hole can spin before it essentially rips a hole in space-time.
A black hole can rip a hole in reality. That's both terrifying and fascinating.
It's a pretty mind-boggling concept.
Okay.
But essentially, general relativity sets the speed limit for black hole spin.
I see.
The SMF RVS model, on the other hand, suggests this limit might be different, allowing for even faster spins. So if we observe a black hole
spinning faster
than Einstein's theory allows,
that would be
a big point
in favor of
the vacuum push idea.
So it's like Einstein's theory says this is as fast as you can go.
Yeah.
And the SMF RVS model is like, hold my beer.
Yeah.
I like it.
Yeah.
What other clues?
We can also look to the cosmic microwave background radiation.
Cosmic microwave background radiation.
Which is like a baby picture of the universe.
Okay.
From just after the Big Bang. It contains subtle patterns.
That could reveal
whether the Big Bang was a singularity.
As predicted by Bang?
As predicted by general relativity.
Okay.
Or a more gradual
finite genesis.
As suggested by the SMF RVS model.
So we could actually see echoes of the Big Bang imprinted on this radiation.
Exactly.
And that could tell us which theory of gravity is more likely.
It's like we're examining the universe's birth certificate.
To see
if it matches the story told by Einstein or this new model.
This is incredible. Are there any other tests?
There's one more.
Okay.
And it's perhaps the most mind-bending of all.
Give it to me.
The idea of post-merger echoes from black holes.
Okay, now you have my full attention.
Right.
Black holes producing echoes.
Yeah.
How is that even possible? They're supposed to be inescapable gravitational sinks.
That's the prevailing view.
Based on
general relativity.
Yeah.
But if black holes actually have this push-based interior,
Okay.
as suggested by the SMF-RVS model,
Instead of
a singularity where everything gets crushed,
right.
then the event horizon, the boundary of the black hole, might not be as absolute as we think.
So you're saying that some gravitational waves might actually be reflected back from inside the black hole, creating these faint echoes.
Pretty wild idea.
Wild idea.
But the SMF-RVS model leaves open that possibility.
Okay.
Imagine shouting into a cave.
Okay.
You hear the initial echo.
Yeah.
But if there's a surface inside reflecting the sound,
Yeah.
you might hear fainter echoes afterward.
Okay.
Similarly, if black holes have a push-based interior,
Interior.
they might reflect gravitational waves,
Yeah.
creating faint echoes after the main signal
From
a black hole merger.
That would be like finding a hidden room inside a supposedly solid wall.
Exactly.
Wow.
And if we could detect those echoes,
That would be huge.
it would be a revolutionary discovery.
Yeah.
That would challenge our very understanding of black holes.
Totally.
It would be a major win for the SMF-RVS model.
This is also fascinating.
So we got these potential clues.
Super spinning black holes.
Echoes from the Big Bang and echoes from within black holes themselves.
That could help us crack the case of gravity.
Right.
But even if these future observations don't immediately point to one model over the other, the fact that we have two very different theories that can explain what we see now is pretty mind-blowing in itself.
Absolutely. And what's really intriguing is that the SMF-RVS model
isn't just limited to explaining gravitational waves.
It
also offers
explanations
for other astrophysical phenomena, like those strange mountains on neutron stars, and the way binary pulsars gradually spiral toward each other.
Wait,
hold on.
Mountains.
On neutron stars.
Those things are incredibly dense.
I know.
Like a city-sized atomic nucleus.
Yeah.
How do mountains even form on something like that?
I mean, story for another deep dive, perhaps.
Yeah.
But the point is that the SMF-RVS model,
even though it's based on this radical vacuum push idea,
seems to be
remarkably consistent with observations across a range of phenomena.
I can't wait to hear more.
So for our listeners who are trying to wrap their heads around this whole vacuum push concept, can you give us a few specific examples from the source material that illustrate how it actually works?
Yes, please.
Sure.
All right.
Now, the source material does delve into some pretty complex equations.
Okay.
But essentially, what they show is how the interaction between the subtle magnetic field and the vacuum scalar field, remember?
That's what SMF-RVS stands for.
That's what SMF-RVS stands for.
Yes.
Can generate a wave that propagates outward, carrying energy and momentum.
So even though the math is complex, the basic idea is that these two fields interact to create a kind of pressure wave.
A kind of pressure wave?
That pushes things around instead of them being pulled
by warped space-time.
As Einstein's theory suggests.
That's a great way to put it.
Awesome.
And what's really cool is that these equations, based on the SMF-RVS model, produce results incredibly close to what general relativity predicts.
Wow.
Even though they start from completely different principles.
So it's like watching two master chefs create the same dish using completely different ingredients and techniques.
Exactly.
Okay.
Right.
I think we've covered a lot of ground here. Where should we go next in exploring this fascinating new perspective on gravity?
You know, one of the most fascinating things about this whole discussion is how much we still don't know about gravity.
It's crazy, right? We've been talking about gravity since, Newton and his apple.
Yeah.
And Einstein revolutionized our understanding with general relativity.
Right.
But now this SMF-RVS model, this vacuum push idea, is potentially on the verge of another paradigm shift. It really makes you question everything you thought you knew.
It's like peeling back
layers of an onion.
Layers of an onion.
Each new discovery
reveals a deeper level of complexity.
And what's so exciting is that we now have the tools and the technology to probe these deeper layers. Like those incredible LIGO and Virgo detectors.
Right.
They can measure distortions in space-time smaller than the width of a proton. It's unbelievable.
Just mind-boggling.
And those are just the current detectors.
I know.
We've got even more powerful ones on the horizon, like the Einstein telescope and the Cosmic Explorer, which will be able to detect gravitational waves from even further away.
Even further.
And with even greater precision.
Exactly.
So it's like
we're upgrading.
We're upgrading from a magnifying glass
to a high-powered microscope.
Yeah.
We'll be able to zoom in and see the universe in a whole new light.
I like that.
And as we zoom in closer, we might find that some of the assumptions we've made about gravity, based on general relativity, need to be revised or even completely overturned.
Makes you wonder.
It does.
What other fundamental aspects of the universe we might be misinterpreting?
It's
it is
a
little unsettling.
A little unsettling, but also
incredibly exciting.
Incredibly exciting at the same time.
At the same time.
A humbling thought.
Yeah.
But it also reminds us that there's so much more to discover.
Yeah.
So much more to learn.
Okay, let's get back to those specific tests.
Right.
That could help us differentiate between the two models.
Mention. Extreme black hole spins, echoes from the Big Bang, and echoes from within black holes.
Right.
Let's break those down a bit more.
Starting with
those super spinning black holes.
All right, so
imagine a black hole spinning incredibly fast.
Incredibly fast.
Now, according to Einstein's general relativity, as a black hole spins faster and faster, it warps space-time around it more and more. But there's a limit. To how much it can distort space-time before it essentially creates a tear in the fabric of reality.
Wait, I'm a little confused.
What does it mean?
What does it mean for a black hole to tear a hole in reality? That sounds a bit...
It's...
like science fiction.
It's a theoretical concept.
Okay.
But it's based on the idea that space-time, the fabric of the universe, has a certain strength.
Okay.
And if you warp it too much... it can become unstable.
I see.
Think of it like stretching a piece of fabric too far.
Okay.
Eventually, it will rip.
Right.
General relativity predicts that a black hole spinning beyond a certain limit would cause a similar kind of rip in space-time.
Okay, I'm starting to get the picture.
So there's a
cosmic speed limit for black holes.
According to Einstein.
But you're saying the SMF-RVS model.
Right.
This vacuum push model. Doesn't necessarily impose...
It doesn't impose that
same limit.
That's right.
Yes.
The SMF-RVS model suggests
that black holes
might be able to spin faster.
Faster than Einstein's theory allows. So if we could observe a black hole spinning faster than that theoretical limit,
that would be
a pretty strong indicator that something else is going on.
Yeah.
That maybe this vacuum push idea has some merit.
Right.
So we need to find those black hole speed demons out there pushing the cosmic limits.
What
about those echoes from the Big Bang?
Right.
Okay.
So remember that cosmic microwave background radiation?
Yes, like a snapshot.
Of
the universe when it was just a tiny infant?
Exactly.
Okay.
And by analyzing the subtle patterns in this radiation, we can test different models of the Big Bang itself.
Okay.
General relativity predicts that the Big Bang was a singularity.
Okay.
An infinitely dense point from which the universe exploded outward. But the SMF-RVS model suggests a finite genesis.
A more gradual, beginning with a finite density.
Precisely.
So instead of an instantaneous explosion,
from a single point,
the universe might have emerged from a more spread out region.
Yeah.
And expanded more gradually.
And those two scenarios, a singularity versus a finite genesis, would leave slightly different fingerprints on the cosmic microwave background radiation.
If we could detect those subtle differences,
exactly,
it would give us a clue about which model of the Big Bang is more accurate.
It's like we're looking for tiny imperfections
in
the universe's baby picture.
To see
if they match the story told by Einstein or this new SMS-RVS model.
I love that analogy.
Okay.
Okay, now for the big one.
The big one.
Those mind-bending echoes from within black holes.
Okay.
This is the one I'm still struggling to wrap my head around.
Wrap your head around.
How could anything, even gravitational waves, escape from a black hole?
It's a challenging concept. And it's important to remember that even within the context of the SMF-RVS model, the idea of black hole echoes is still very speculative.
Okay.
But here's the basic idea.
Okay.
You're right.
Yeah.
The traditional view of black holes, based on general relativity, is that they're inescapable.
Right.
Once something crosses the event horizon, the point of no return. It's gone forever. No light. No information. No gravitational wave can get out.
Right, that's what I always thought. So how does the SMF-RVS model change that picture?
Well, if black holes have this push-based interior, as suggested by the SMF-RVS model, instead of the singularity where everything gets crushed to an infinitely small point, then the event horizon might not be as absolute as we think.
So you're saying that some gravitational waves might be reflected back?
It's possible.
From inside the black hole, creating echoes.
That's the idea.
Okay.
It's like dropping a rock into a pond.
Yeah.
You get the initial splash.
Okay.
And then you might get some smaller ripples.
Reflecting
back from the edges of the pond.
Okay.
But with a black hole,
the
pond is gravity itself. And the ripples are gravitational waves.
Okay, that analogy helps, but wouldn't those echoes be incredibly faint?
You're absolutely right.
And difficult to detect.
I mean, you were talking about signals coming from inside a black hole.
Yeah.
A place where gravity is supposed to be so strong that nothing escapes.
Right.
Detecting those echoes, if they exist, would be a monumental challenge. Requiring incredibly sensitive instruments and advanced data analysis techniques.
But if we could pull it off.
That would be. It would be a revolutionary discovery. It would provide strong evidence for the vacuum push model. And force us to completely rethink our understanding of black holes.
That would be incredible.
It would be a game changer for sure.
Okay.
So we've got these tantalizing clues.
These potential smoking guns
that could help us solve the mystery of gravity.
But even if the SMF-RVS model is based on this radical vacuum push concept,
it's remarkably consistent.
It can explain those gravitational wave signals
that we've seen
from merging black holes and neutron stars.
And it also accounts
for other phenomena like those mountains on neutron stars and the way binary pulsars spiral towards each other.
You're absolutely right.
It's pretty incredible, right?
To bring us back to those points,
I know.
The SMF-RVS model isn't just some wild speculative theory. It has real explanatory power.
Yeah.
And that's what makes it so intriguing.
Okay, so we've got this new model, the SMF-RVS model, that challenges some of our most fundamental assumptions about gravity. It suggests that gravity might be a push force
rather than a pull. Arising from the interaction
between these two mysterious fields, the subtle magnetic field and the vacuum scalar field.
And it makes some pretty bold predictions.
That we might be able to test.
In the coming years.
With more advanced telescopes and gravitational wave detectors.
That's a great summary.
Okay.
And I think it's important to emphasize that even if the SMF-RVS model doesn't turn out to be the final answer, it's pushing us to ask the right questions.
Yeah.
It's forcing us to think critically about our assumptions and to be open to new possibilities.
It's a reminder that science is a process of continuous discovery and refinement.
Exactly.
We're always learning, always testing our ideas against new observations. And sometimes we have to be willing to completely rethink what we thought we knew.
Exactly.
And this is what makes science so exciting.
We're on a journey.
To understand the universe.
And along the way, we're bound to encounter surprises.
Challenges. And maybe even a few revolutions in our thinking.
It is?
Well, this deep dive has certainly been a journey for me.
A journey.
I feel like I've learned so much.
Yeah.
But I also have more questions than ever.
But I guess that's the nature.
Of scientific exploration, right? It's about embracing the unknown and constantly seeking deeper understanding.
You've hit the nail on the head.
Okay.
Curiosity.
And a willingness to question.
Or the driving forces.
Of scientific progress.
Okay. I'm ready to keep exploring. What other fascinating aspect of
the SMF-RVS model
should we dive into?
You mentioned those neutron star mountains earlier,
right.
And I'm really curious to learn more about those.
Let's take a closer look at neutron stars. These objects are some of the most extreme and enigmatic
entities in the universe.
They're the remnants of massive stars
that have exploded as supernovae.
I know they're incredibly dense.
Yeah.
But can you give our listeners a sense of just how extreme these objects are?
Yeah, how extreme are they?
Imagine taking a star
Okay.
many times more massive than our sun.
And
crushing it down to the size of a city.
To the size of a city?
That's a neutron star.
Wow.
A teaspoonful of neutron star material.
A teaspoonful?
Would weigh billions of tons.
Oh my gosh, okay.
So they're unbelievably dense.
So dense. What does that have to do with mountains?
What does that have to do with mountains?
How can something so dense even have surface features like mountains?
That's a great question.
It's a big question.
And it gets to the heart
of how
the SMF RVS model differs from general relativity. Remember, the SMF RVS model proposes that gravity is a push force.
Okay.
Now, in the context of neutron stars,
this
push
can actually
create variations in density within the star.
Wait, I thought neutron stars were supposed to be incredibly uniform.
Yeah.
Like almost perfectly smooth spheres of ultra-dense matter.
Right.
How could there be variations in density?
That's the classical view based on general relativity.
Right.
But the SMF RVS model introduces a new wrinkle.
Okay.
Because gravity is a push in this model.
Yeah.
The intense pressure at the core of the neutron star can create subtle variations in density throughout the star.
Okay.
It's like squeezing a balloon.
Yeah.
You might create bulges or bumps.
Depending
on how you apply the pressure.
So you're saying that this vacuum push can create regions within the neutron star that are slightly less dense than the surrounding material.
Exactly.
Okay.
And these less dense regions, even though they're still incredibly dense compared to anything we experience on Earth, effectively create mountains on the surface of the neutron star.
So these mountains aren't like the Rocky Mountains we have on Earth.
They're more like
subtle bulges or bumps.
Caused by variations in density
within the neutron star itself.
Precisely.
Wow, that's incredible.
And here's where it gets really interesting.
Okay.
These neutron star mountains, even though they're tiny, compared to the size of the neutron star, can actually have a measurable effect on the star's rotation.
Wait, you're saying that these tiny bumps,
I am,
these density variations,
can actually change how fast a neutron star spins.
How is that even possible?
It's all about angular momentum. As the neutron star spins, these mountains create tiny asymmetries.
No, it's gravitational field.
In its gravitational field.
So these mountains create a kind of gravitational wobble.
You got it.
As the neutron star rotates.
And this wobble,
although
incredibly subtle,
can be detected
by observing the way
the neutron star's pulses change over time. Okay, so I'm trying to put this all together.
Yeah.
The SMF RVS model,
with its vacuum push,
gravity predicts that neutron stars can have these subtle density variations
that create mountains.
These mountains cause a tiny gravitational wobble
that affects the neutron star's rotation.
And we can actually detect this wobble by observing the star's pulses.
You nailed it.
Did I get that right?
You nailed it.
Awesome.
And the fact that we do observe these subtle variations in neutron star rotation provides further support.
For the SMF RVS
model.
It's another piece of the puzzle. That fits into this new picture of gravity. This is all so mind-blowing. It's incredible how these seemingly abstract theoretical
ideas can have such tangible, observable consequences.
I know.
I can't wait to see what other surprises the SMF RVS model has in store for us.
But I think we've covered a lot of ground in this deep dive.
I think so, too.
And I want to make sure that our listeners have a chance to digest all this amazing information.
All right.
I know it's a lot, but okay, so for our listeners who are feeling a bit overwhelmed by all this cosmic mind-bending, one key takeaway
you'd want them to remember.
Yeah.
I'd say the most important takeaway is this.
Okay.
We're living in a truly extraordinary time for scientific discovery.
It really is. An incredible time to be alive, especially for those of us who are fascinated by the universe and all its mysteries.
And completely agree.
Yeah?
The nature of gravity is one of those mysteries.
Yeah.
And this SMF-RVS model,
Ah,
with its idea of gravity as a push
push
force,
force.
offers a really compelling alternative
Oh,
to our current understanding.
yeah.
Whether it turns out to be the correct explanation or not,
Yeah.
it's pushing us to think in new and exciting ways
About
about the fundamental forces that
Mhm.
shape our universe.
It's a good reminder that even our most established scientific theories
Hmm.
are constantly being challenged and refined as we gather more
As we
evidence
gather more
and
evidence.
explore new possibilities.
Exactly.
Yeah.
Science is a journey, not a destination.
Oh.
And in this case, the journey is taking us deep into the heart
Of-
of some of the most profound mysteries in the cosmos.
So,
Yeah.
if this vacuum push idea does turn out to be true,
Yeah.
what would it mean for our everyday lives? Would our apples start falling up?
That's a great question.
Yeah.
And it gets to the heart of how science works.
Okay.
Even if the SMF-RVS model is proven correct,
Uh-huh.
it doesn't invalidate the incredible successes of general relativity. Remember,
Yeah.
both models make very similar predictions for
For-
most everyday phenomena.
So we wouldn't suddenly be floating off into space.
No.
Okay, good.
Gravity, as we experience it,
Yeah.
would still work pretty much the same way.
Okay.
The differences between the models only become important at extreme scales,
Yeah.
like near black holes in the
Ah.
very early universe,
Yeah.
or when we're trying to make ultra-precise measurements,
So it's more about refining our understanding of the underlying mechanisms of gravity
rather
than completely rewriting the rules of the game.
Exactly.
Yeah.
Think about it like this.
Okay.
Newton's laws of motion work incredibly well
Hmm.
for most everyday situations.
Yeah.
But when things start moving really fast, close to the speed of light,
Sure.
we need to use Einstein's theory of relativity
To get an accurate picture.
to get an accurate picture.
It's not that Newton was wrong.
Right.
It's just that his laws are a special case
That apply
that apply in certain limited circumstances.
in certain limited circumstances.
Ah, so the vacuum push idea might be like a more general theory of gravity.
That's a very insightful way to think about it.
Okay.
And it highlights a key point.
What's that?
Scientific progress often involves building upon and refining
Refining.
previous theories,
Yeah.
not necessarily discarding them completely.
It's like adding new chapters to a book.
Exactly.
Rather than throwing the whole book away.
And those new chapters can open up whole new worlds of understanding.
Imagine.
Imagine the implications if we could harness this vacuum push force.
Could we develop new technologies? Perhaps even new forms of energy?
Now you're getting into science fiction territory,
I know.
but I love it.
It's fun to think about.
It just goes to show how exploring these fundamental questions about the universe
Yeah.
can spark our imagination and inspire us to think beyond the limits of what we currently know.
Absolutely.
And even if we don't find all the answers right away,
Yeah.
the process of asking these questions,
Designing experiments, analyzing the data.
designing experiments, analyzing the data is what drives scientific progress
And pushes the boundaries of human knowledge.
and pushes the boundaries of human knowledge.
So, for our listeners who are still wrapping their heads around all of this mind-bending physics,
What's the one thing?
what's the one thing you'd want them to take away from this deep dive?
I think the most important takeaway is this.
Okay.
We should never stop questioning and exploring. The universe is full of mysteries.
Yeah.
And the pursuit of understanding is one of the most rewarding endeavors that we can undertake.
It can undertake.
The SMF-RVS model,
Wow.
whether it stands the test of time or not,
Yeah.
is a testament to the power of human curiosity and our relentless drive to make sense of the world around us.
That's a beautiful thought.
So,
So as we conclude this deep dive,
yeah.
I encourage all of you to keep looking up at the stars
Yeah.
and pondering the mysteries of the universe.
Who knows what incredible discoveries await us in the years to come.
Indeed, the future of scientific exploration is filled with possibilities.
And I have a feeling we're just scratching the surface
I have a
of what we can learn about the universe and our place within it.
Well said. And on that note, we'll wrap up this deep dive into the fascinating world of gravitational waves and the vacuum push theory of gravity.
Until
Until next time, keep those brains buzzing and those imaginations firing.